I'm Hannah.
And I'm Emily.
And today we're going to give you an AP Chem review of gases.
Enjoy!
Okay, first we're going to talk about some basic gas laws. We'll start with Boyle's law, which states at a constant temperature, pressure and volume have an inverse relationship. So when pressure increases, volume decreases, and when pressure decreases, volume increases. So you can see we have a little equation, PV equals constant. So when temperature is constant, PV have an inverse relationship. We're going to do a demo to explain Boyle's law in a second.
To illustrate Boyle's law, we're using a bell jar vacuum and a bag of marshmallows. First, we're going to stack the marshmallows in a pyramid shape so that it's easy to see the change in volume that will occur. The purpose of the bell jar vacuum is to remove pressure from the inside of the bell jar. When the lid is placed on, a tight seal is formed between the bell jar and the stand. When the vacuum is turned on, pressure is removed from the inside of the bell jar. As pressure decreases around the marshmallow, pressure inside becomes greater than the pressure outside of the marshmallow. Therefore, we can see the volume of the marshmallows is increasing. This shows that as pressure decreases, volume increases. When the marshmallows have reached their maximum value, we unplug the vacuum and watch them shrink back to their original size. This shows that as pressure increases within the vacuum, volume decreases. When the bell jar lid is removed, we can see that the marshmallow is actually smaller than the control that was not expanded and shrunk.
Next is Charles' law, and this states the relationship between temperature and volume. As temperature increases, volume also increases, and we refer to this as a direct relationship as long as pressure is constant throughout.
Okay, for Gay-Lussac's law of combining volumes, it states that at a given temperature and pressure, volumes of gases react in small whole number ratios. So, for example, carbon dioxide will always form with one carbon atom and two oxygen atoms. Now we're going to give you a brief demo to illustrate this.
First, we're filling up a pop can about a third of the way with normal tap water. Next, we put it on a hot plate to boil, which takes about 5 minutes. Next, we quickly invert the hot pop can into a beaker of cold water. As you can see, the pop can is crushed. This happens because the temperature decreases, so the pressure on the inside of the can was lowered, causing the...
This brings us now to Avogadro, whom you might be familiar with for his famous determination of the mole, 6.022 times 10 to the 23rd. He also did a lot of work with gases, and he created a famous hypothesis that states that equal volumes of gases at constant temperature and pressure contain equal numbers of moles. Said a different way, this can be said that volume is directly proportional to the number of moles, as long as they're at a constant temperature and pressure.
When we combine all these gas laws, we find ourselves with the ideal gas equation, PV equals nRT, also known as Pivner. P stands for pressure, V for volume, N for number of moles, R is a gas constant, and T for temperature in kelvins. We can use this equation to solve for any of the variables, or we can manipulate it to find density, molar mass, or the mass of the gas.
Now that you know how to solve for all the pressures of different kinds of gases, you may want to be able to combine the pressures. This brings us to Dalton's law of partial pressures, which states that total pressure is equal to pressure of gas 1 plus the pressure of gas 2, etc., etc. And this assumes that the gases do not react. This also goes for the number of moles, stating that the total number of moles is equal to the moles of gas 1 plus the moles of gas 2, etc., etc.
Another main part of gas laws is the kinetic molecular theory that explains why gases behave the way they do. There are 5 main postulates of kinetic molecular theory, the first being that particles are in random continuous motion. Second, the volume of particles is negligible to the entire volume of a gas. 3, attraction and repulsion between particles is negligible. 4, the average kinetic energy is unchanging, although individual energies can change. And that 5, average kinetic energy is proportional to temperature. So as temperature increases, average kinetic energy also increases. As I hinted at earlier, individual gas molecules have a wide range of speeds at any given moment because there are frequent collisions between molecules. Root mean square speed, denoted as U, is the speed of a molecule possessing average kinetic energy. RMS speed increases as temperature increases. In fact, absolute temperature is a measure of average kinetic energy.
Gases don't like to be contained, and effusion describes what happens when gases escape. Effusion is the escape of a gas through a tiny pinpoint, such as gas leaking out of a balloon through a hole. Similarly, diffusion is the spread of a gas throughout a space or another substance, such as when you spray a perfume bottle and the scent eventually fills the entire room. Graham's law describes that molecules with smaller molecular weights effuse and diffuse more quickly than molecules with higher molecular weights.
So, for all this time, we've been talking about ideal gases. And sorry to lie to you, but real gases aren't ideal. At high pressures or low temperatures, gases actually deviate greatly from ideal behavior, described by Pivner. They have a finite volume, although small, and they do attract and repel each other, though not normally very much. Van der Waals equation is similar to Pivner, you can see up here, and it corrects for these small differences.
Ta-da!
The
end!
Yeah, they tried to make it manly looking, but of course, see, the guys look like this.
No, didn't work.
Like this.
Okay.
And farther.
No, it didn't work. Oh, not really.
They tried to have
Oh no!
Okay, well then we're filming over that. It worked the first time, but did not work this time.
We can do a little